This is a video from section 12.5 and it's based off the lecture notes. Let's take a look at example 3. Determine whether the lines L1 and L2 are parallel, skew, or intersecting. If the lines intersect, find the point of intersection. Skew just means that the lines are neither parallel nor intersecting. So L1 is given by the parametric equations x equals 5 minus 12t, y equals 3 plus 9t, and z equals 1 minus 3t. Now, v1 is the vector negative 12, 9, negative 3, and v1 is a vector that runs parallel to line 1. Now, how did I come up with this vector? Now, to get the x component of negative 12, we go to the parametric equation x equals 5 minus 12t, and we read off the coefficient of t, which in this case is negative 12. To get the y component of 9, we go to the parametric equation y equals 3 plus 9t, and read off the coefficient of t, which in this case is 9. And to get the z component of negative 3, we go to the parametric equation z equals 1 minus 3t and read off the coefficient of t, which in this case is negative 3. And so that's v1. Now, L2 is equal to this. So it's the parametric equations x equals 3 plus 8s, y equals negative 6s, and z equals 7 plus 2s. And so v2 is a vector that runs parallel to line 2, and that's given by, again, the vector 8, negative 6, 2. And again, I do the same thing. To get the x component of 8, I go to the parametric equation x equals 3 plus 8s and read off the coefficient of s. To get the y component of negative 6, I go to the parametric equation y equals negative 6s and read off the coefficient of s, which is negative 6. And to get the z component of 2, I go to the parametric equation z equals 7 plus 2s and read off the coefficient of s, which in this case is 2. Now, if we notice, v1 is equal to negative 3/2 times v2. So v1 is a scalar multiple of v2, and so that tells me v1 is parallel to v2. So I drew a picture over here where I indicated that v1 and v2 run parallel. By design, v1 is parallel to line 1. And v2 is parallel to line 2. So if v1 and v2 run parallel, it has to follow that line 1 and line 2 run parallel to each other as well from the picture. And so we can then conclude that L1 is parallel to L2. And that's how we work example 3. Let's take a look at example 4. Determine whether the lines L1 and L2 are parallel, skew, or intersecting. If the lines intersect, find the point of intersection. So L1 is given by the symmetric equations x minus 2 over 1 equals y minus 3 over negative 2 equals z minus 1 over negative 3. And so to get the vector that runs parallel to line 1, we just have to look at the denominators. And so v1 will be given by the vector 1, negative 2, negative 3. So you notice it's 1, negative 2, negative 3. 1 is the x component, negative 2 is the y component, negative 3 is the z component. For line 2, it's given by the symmetric equations x minus 2 over 2 is equal to y minus 3 over negative 2 is equal to z over 7. And so v2 is equal to the vector 2, negative 2, 7. And so V2 runs parallel to line 2. Now, L1 is not parallel to L2 since V1 is not parallel to V2. Now, how do I know that? Because I know that V1 is not a scalar multiple of V2. Okay? Do L1 and L2 intersect? So I'm going to set up a system of equations. So if we go to line 1, so let's go back here. I'm going to take x minus 2 over 1 and set it equal to y minus 3 over negative 2. And for line 2, I'm going to take x minus 2 over 2 and set it equal to y minus 3 over negative 2. And that's exactly what I did over here. So I have a system where I'm going to solve for x and y. And when we do, we get x equals 2 and y equals 3. Now, the question then becomes, if I go to line 1 and plug in x equal 2 and y equal 3, and then if I go to line 2 and plug in x equal 2 and y equal 3, will it produce the same value of z? If the answer is yes, then we can say the lines intersect. If the answer is no, then the lines do not intersect, and then we can say that the lines are skew. So let me say that again. I'm going to take x equals 2 and y equals 3, and I'm going to plug those values into the symmetric equations for line 1 and line 2, and I'm going to solve for z. If I get the same value of z, okay, then that tells me that the lines intersect. If I get different values of z, that tells me that the lines are skew. So when we come over here, now when x is 2 and y is 3, it's going to follow that z equals 1. So notice, when x is 2, 2 minus 2 is 0. When y is 3, 3 minus 3 is 0. And when I solve for z, basically I'm taking z minus 1 and setting it to 0. The denominator won't make any difference in this context. And so it's going to naturally follow that z equals 1. If I go to line 2, when x is 2 and y is 3, the only possibility for z is for z to equal 0. And that's exactly what happened. So notice how in the first line I got z equals 1. In the second line I got z equals 0. That's a problem. And so therefore L1 and L2 do not intersect, and then it follows that L1 and L2 are skew. So if the lines are not parallel and they do not intersect, the only possibility is for those lines to be skew. And that's example 4. Now, let's take a look at the equation of a plane. We need a specific point P sub 0, which is equal to x sub 0, y sub 0, z sub 0 on the plane. We also need a vector n, which is equal to ABC, that is orthogonal or perpendicular to the plane. Let P equal xyz be an arbitrary point on the plane. Now, let r sub 0, the vector r sub 0, and the vector r be the position vectors of P naught and P respectively. And so if you notice, I have a plane. Think of a plane as like a sheet of paper that extends forever in all directions. Or, well, let me say, it extends forever north, south, east, and west. So it's, if you lay it flat. Now, notice here, n is perpendicular to the plane, right? P naught P is a vector that lies in the plane. Now, by design, n is perpendicular to the vector P naught P. And that's exactly what we have over here. Now, r minus r naught is equal to the vector p naught p, which is equal to x minus x naught, y minus y naught, z minus z naught. So it's equal to that vector. Think terminal minus initial. If I take n and dot it with p naught p, I get 0. But remember that n is the vector ABC. P naught p is the vector x minus x naught, y minus y naught, z minus z naught. So the vector ABC dotted with the vector x minus x naught, y minus y naught, z minus z naught is 0. And from the definition of the dot product, that tells me A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to 0. And this is the first equation of a plane that you get exposed to. And that's a very important equation that will come up again in chapter 14. Okay? And so that says, if we take this a little further, ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. Now, this says ax plus by plus cz minus ax naught minus by naught minus cz naught is equal to 0. But that's pretty complicated. And so what I'm going to do is I'm going to let d equal negative ax naught minus by naught minus cz naught. So it's going to simplify the equation of a plane. And so therefore, we can express the plane as follows. ax plus by plus cz plus d equals 0. And that's going to conclude this video for section 12.5. And again, this is based off the lecture notes. Okay, thank you.